like what are the various timing aspects, right? Like we started with the very basics, like setup time evaluation, hold time evaluation, synchronizations. So today's session is, some part like will be timing as well. With that, like how the setup violation, hold violation will be produced, like when it occurs and how we can resolve. Along with that, like as agenda of today's session is like debugging part. So we'll also discuss like how you can debug in a given FPGA design. So simulation is fine, but let's say like in the real time scenario, when you want to debug it on FPGA board, how we can debug. So for that, actually, like we will be using two hardware. So one of the hardware is this one. Uh, is it visible? So this is actually, um, I think I have to remove my back blurring. Yeah, I think now it should be fine, right? So this is one of the hardware what we'll be using. So this is a Kriya SOM from AMD. So it has a Zinc Ultra Scale FPGA. Okay, so like where you can actually go for high speed design. So this is one of the board what we'll be using for today's experiment. Um, Another board, what we have is this board. This is actually Altera based FPGA. It's a Max 10 CPLD, I can say. This is designed by us itself. I mean, like at Anmaya Technologies, we have designed. So in this board, we will be testing some of the things. I mean, basically Altera based experiment. Okay. So on these two boards, we will be discussing today's session. So, I mean, initially we will see with the Xilinx FPGA, like how it works and using Vivato, how we can put signal tap and analyze. Before that, like, let me give you a brief uh, idea. What is signal tap or like signal analyzer we say logic analyzer. So let me start with that part. Then, like we can start designing a simple counter in FPGA. And with respect to that counter, what we will do is we will understand uh, the timing aspects. Initially, I'll also show you that like how the timing will be impacted there. And the same thing we will connect to ILA and see the behavior, how it is in the board, right? So how it is behaving. So like we will, I mean, it will be like maybe whole session will be on the single experiment uh, with the different aspects of it. Okay. With that, I'll also explain a little bit on because the Kriya SOM board what I have, it's a SOC, right? So system on chip, where I can instantiate one ARM processor and I can also test my software part of it, right? We'll start with that, like what is SOC, Kriya SOC, what I have, what is the board I have shown you. From that point, how I can design my architecture and how I can debug and how I can produce one timing issue in that code and I can resolve that. Okay? That is the whole objective of today's session. Let's get started. Hope my yes. So whenever I say SOC FPGA, right? So previously we used to have only FPGAs. I mean, like if you see Kintex FPGAs, Vertex FPGAs. I mean, nowadays also you get that standalone FPGA. One of the board what I have shown you, that Max 10 board, that is also a standalone FPGA. That doesn't have anything. It has some resource block like logic. blocks. Yesterday, what I have discussed, lookup table, block RAM, flip flop. It has only that. But when I talk about SOC, it has some processor. And I will also have FPGA. Okay. So this processor and FPGA basically interface using AXI interface. Clear? So this together we call it as system on chip SoC. Okay. Processor, FPGA, and in between AXI interface. So together we will call it as SoC. So now we will see how to design this. Okay. So now we will start designing this part. Okay. Let me open Vivado. So one thing you have to notice, so this processor part, right, in like MPSoC, we will be having ARM processor, ARM Cortex processor. It will be again, it will be quad core, dual core, depending on the application, which FPGA you choose, which SoC you choose. So in Altera-based FPGAs like Intel or in case of Micro Semi, they have their own version of SoC. So in Intel, they call it as Agilent static, right? These FPGAs basically comes with the SoC. They also have ARM. So this is hardcore I'm talking about. So there are like some concept of softcore also. We have something called microglaze SoC. So that like where with the FPGA itself you can instantiate this. Okay. Like let me just create a fresh project. I mean, previously what I had shown you that like I mean some random part number I had chosen. So today we have to choose the create SoC part. So here in the boards, These are the evaluation board. I mean, like in your college, you may use that board, or you may have pink board. So various boards lists are available. So in my case, it is Kriya SOC. The part number is KV 260 Vision Starter. Okay, AI Starter Kit, Vision AI Starter. So we have to choose this board and finish. So you can see automatically this board is selected, right? We chosen. So all the part number, like you can see what is the project part and all the constraints, everything it will be automatically selected. Now I said I have to interface this processor to FPGA. I mean, like this is like not only FPGA, FPGA. So one thing, can you tell me if I want to program FPGA, which language we are using in our lab? Verilog, right? Verilog VHDL. But can I program processor with Verilog or VHDL? No, right? So I need to use C, C++ kind of thing. So in terms of tools also, it will be split across these two. Okay. So now processors usually like we use VT tool. Okay. So like we have SDKs or VTs. So the processor will be programmed using VT's tool, and this FPGA part will be programmed using Vivado. And how we will come to know like the interface, like let's say I want to write some logic on the processor side and I want to control some part of FPGA through processor. So in that scenario, we usually use AXI bus, right? So, but how FPGA comes to know that processor is controlling, because these two are independent entities, right? So we go for some kind of memory mapped interface. And also we have to generate something called board support package in the FPGA. Board support package, which says what are the controls required from the processor to FPGA. Clear? Um, let's say here, for that purpose, right? Whatever like interfacing purpose, we have to create a block design. Okay, so first we need to create a block design. This is the first stage. I mean, whenever we are dealing with the processor and FPGA together, right? So we have to deal with block design, create new block design. Uh, by the time it creates the block design, can someone tell me uh, in a same chip, why do I need processor and FPGA? Why? I mean, in FPGA itself, I could have done some uh, computation and like I would have like implemented that, right? But why I need processor in certain case? Why I need SOC kind of scenario? What is the need of? So if you see this architecture, I use processor also, I use the FPGA also, right? What is the need of it? Can someone unmute and tell me? What could be the need? I mean, based on your perspective, what could be the need? I mean, processor plus FPGA. You have when in masters usually those who have taken VLSI, you might have gone through the subject hardware software co-design, right? Why do I need hardware and software co-design? Have you all seen these kind of devices in your lab? I think now most of the colleges has this sync SOC, right? I don't think. You might not have seen this. So all, I mean, as far as I have seen, like all the college wherever I've said, so at least Z board will be there, right? So Z board is the SoC, right? So it's not just FPGA. We often misunderstand that only FPGA, but it is not FPGA. It's actually a SoC, system on chip. It has processor also. It has FPGA also. But why do I need that? Yeah, Partha sir is saying it is like area, speed, and power. Yes, that is true. But there is a specific reason behind it. The speed is one thing. Uh, any specific answer can I get? In which application have you seen this? Some things running on the processor side, something running on the FPGA side. So, uh, see, like when I say I'm implementing everything on FPGA, it's basically a RTL based implementation, right? But one thing, like there is always like all the applications, right? Need not be the RTL based implementation. Let's say like I need to read one temperature value from the temperature sensor. Whether my speed is important there? No, right? So I can go with like very slow speed implementation as well. So in such scenarios, what I can do is like I can go with processor implementation. So when I say that like my architecture requires lot of power, I mean a lot of uh, speed. In that case, like I can accelerate by putting the whole architecture into FPGA. But whenever the speed is not important, whenever I can go for very slow speed application, then I can put the whole thing into processor side. Because every line of the RTL, what I write in FPGA, right? So that is going to be created as some kind of circuitry. And that circuitry is consuming power. And again, it is consuming a lot of area. But whereas uh, 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 whatever I put it into the processor side, it is not consuming any area as such. I mean, it is reusing the existing architecture each time, right? So, but in case of uh, FPGA, every time I add new logic, it is going to consume some area, right? So that is one of the reason why I put the whole architecture into. I mean, I split the architecture into processor and FPGA. As a system designer, right? Whenever like we architect the systems, so first we identify which components I have to put it into FPGA, which components I need to put it into the processor side. So once that division is done, right? So then like we implement it. So some part we will be putting into processor side. And let me consider another example. Let's say in some cases you have to run some operating system, real-time operating. So that real-time operating system you cannot put it into FPGA, right? So let's say like some usually these operating systems will be million lines of. So that whole million lines of code you cannot implement RTL for, right? Some part you have to put it into processor itself. So nowadays, like we have lot of open source um, APIs are available, OpenCL, OpenGL, like image processing API, TensorFlow. Those FPGA equivalent is not available. You cannot put those libraries into FPGA also, right? So what usually I do, many a things I run it on the processor side, right? Let's say like one image processing application. For me, writing a image processing sequence is easy in the processor side. So all the image processing application I put it on the processor. And in that, let's say convolution neural network is taking lot of time. Okay, convolution neural network. Usually, you know that like it is a large set of convolutions, right? I mean, you have to do a lot of mathematical operations there. So that if it is taking a lot of time, what I do, I implement convolution neural network on the FPGA side. Through DMA from processor to FPGA, I send the data. I perform that convolution neural network and I send it back the result to the processor. So what it happens like this FPGA architecture It will act like one of the instruction in processor. Like let's say add instruction. What happens? That two data will go to the ALU, and in ALU those two numbers will be added and result will be sent back to one register. Same way in the processor, you have two images. Now you want to perform some convolution neural on that two images, or like you want to identify the image, facial recognition you want to do. If you do it in processor, everything like fetch, decode, and then like every cycle by cycle, that in sequential manner that execution will happen, right? So it will go to ALU, it identifies each pixels, it processes on each pixel, then goes back to FPG. Then finally we will get a result. That takes a lot of time. But here in FPGA, I can implement parallel, like let's say 1024 elements parallelly I can implement, right? So that 1024 matrix multiplication, like in maybe like 10 clock cycle, 20 clock cycle I can. Previously, it might have taken like some 1,000 clock. Now it reduced to 20 clock. What I do, I'll push all the data to FPGA. I process that in few clock cycle. I send back the result to the processor. So that is why FPGA usually we say it as the accelerator. I mean, we have to look FPGA in two perspectives. For VLSI industry, it will act like an emulator or prototyping device. But as an application point of view, let's say like I want to use it for defense application. If you want to use it for like autonomous vehicle application, in that scenario, these devices will act like a accelerator, right? Uh, like in some of the colleges, you might be already having this hardware accelerator subject. Usually, these subjects like specialized subjects will be there in masters, right? So hardware accelerator, basically you learn like how you can actually accelerate part of the design so that you can process at the higher speed, right? So now here, like when you clicked on the create block design, so first what you do, you create block design. So this create block design, what it does is, so all the Verilog code what you write, that is in FPGA. Whatever the processor code you write, that is in SDK, right? I mean, like you write a C program for that. So in block design, you create an interface between processor and FPGA. How you have to talk from processor to FPGA. I said that like I want to send the data to the convolution neural network. So I have to define some address, right? I mean, like whenever I say that like convolution neural network, so processor should know where that convolution neural network is present. How I can, in what way I can write to that convolution neural network. So that interface I will be building here in the block. Clear? So first you have to create, like here plus button you will see, right? So you have to click on that. So then it will show various options, like multiple options you'll see. So then you have to add Zinc Ultra Scale MPSOs. So this particular part you have to select Zinc Ultra Scale MPSOs. So once you add this Zinc Ultra Scale SOC, so usually you will get this option, Run Block Automation. Click on that. So these are the bus ports. Okay. So like whatever you want to like locally interface, right? So these are the buses. So using this bus, you can talk to processor. Okay. So ideally, when I say that like I'm adding this processor, right? So it doesn't mean that like I'm creating this processor on the FPGA. It is already existing. This processor is hardcore. Okay. So that is already existing in the FPGA. What I am doing is I am establishing the interface. So if you see the address editor here, so it will keep adding addresses for communicating to the FPGA. Okay. So I can make this as external. So you have to see here. Everything is generated, right? Now, yesterday I said you like one scenario uh, that you have FPGA. So the clock is coming from external oscillator, right? External oscillator. So this was the scenario. But in whatever the board I have shown you, so it is correct. I mean the same scenario, but here I have two components, right? I have PS, that is processing system usually. So the processor part usually in FPGA we refer it as processing system part, PS, and FPGA part we refer it as PL, programmable logic. Programmable logic. So this part we call it as processing system. Okay. Now what I have to do is like, I mean, in the architecture, how it is basically is, so to the processor side, they have connected high speed clock. So in the processor, we have internal PLL, and through that PLL, I can take that clock into PL side. Okay. So that architecture, you can see it here. So this PL clock one, whatever it is coming out, right? So that is coming from the processor side. So you can use this clock internally for your operation. Okay. So if you double click on this, so you can you see this? This is the internal architecture of Zinc UltraScale FPG. That is SoC. So here, right? So in the clock configuration, you can say that like what should be the clock. So input reference clock. So PSS reference clock, it is actually 33.33 megahertz. Okay. So that is for the processor. Okay. So PL fabric clock. You can see PL0 clock that is actually generating 100 megahertz, 99.9. So there will be small variation in the clock frequency. But again, that is actually like exact clock we cannot generate, right? Because you know that like we are like input clock, whatever the clock it is connected through crystal, that is 33.333. So if you want to make it exact 100, that multiplication division factor will not be available. So that is why we will not be able to generate exact 100 megahertz clock. That there is like I can say 0.001% error is there in the clock. But still, that is, I mean, if it is not timing critical application, still that is acceptable. Okay. So now that clock is coming out. So now this is the SoC architecture what we have, right? First stage after you create a block design, what you have to do is you have to create the wrapper for it. Right click on this design and create HDL wrapper. So this HDL wrapper where you can actually interface your Verilog code. Okay. So this will create a wrapper. I mean, like this is a component for us. I mean, this is like this processor will act like a component. You know that instantiation concept, right? You have a module. If you want to instantiate that module in your Verilog code, you call that module, right? So the same way, you can think the whole block design as one module. It is a processor. If you want to communicate that with that processor, what you have to do, you have to instantiate that in your design, and you have to interface to your local Verilog code, right? That way we can interface. So let me just remove this external part. I mean, I need only clock. Okay. So let me, so before that, you have to validate this also. So there is no error. So then I can generate the wrapper. So usually you have to validate. I mean, there was one error. So you have to validate. There is one validation option. So if there is no error, it will create a HDL wrapper. Because I haven't added any local peripherals, it was showing error. So I'll just remove that. I just need clock actually. I mean, for my counter, from the processor, I will take clock. I will not interface the software side. I mean, as I discussed, so software discussion is out of scope for us as of now. So what I'll do, I'll just interface this. I'll create a wrapper and I'll interface this whole thing into my design. Now you can see this Verilog code automatically created, right? If you open this Verilog code, you have these clocks, you have, so this whole thing is created as one component, right? So now you can see this PL clock one. This is the clock output where it is coming, correct? So this is the clock output for us, and we have all the peripherals. So now this is actually like whatever the diagram we have. So this is actually a processor. So we interface this processor to the FPGA side. This is the PSPL interface what we have done, correct? So now what we have to do, we have to create one. Let's create one small counter logic, okay? And let me not create any ports as such. So this FPGA doesn't have any port. I mean, like in the sense, like everything I'm taking from the processor. So let me remove all these things and use only logic directly. Always at pause edge of this clock, PL clock 0. What I'll do is I increment one counter. Okay. This is my logic, simple logic. So my clock is coming from which part? Processor. What is the frequency of clock I said? It is 99.99, right? So which is like generated from the processor. And that clock, I am based on that, I am implementing some simple count. Okay. So this is the basic interface what I have done. So now you can see that with respect to this diagram. So my counter logic is implemented on the FPGA side, right? So here it is counter is implemented, and clock is coming from the processor. Okay. Let's say based on this counter, okay, counter value, if I want to implement any logic in the processor side, okay. So I know this is exact timer what it is running. So I can take it into the processor. I can run some logic in the processor, right? So for that, again, you have to create one interface. I mean, if I want to do that kind of logic, what I have to do? I have to create one interface here. You have to go to this, and maybe you have to add some, let's say like add IP. I can say GPIO, AXI GPIO. So This simple logic I'm telling how to interface. So this GPIO, right? You can make it 8-bit. That counter you can connect to this GPIO. This axis you can connect to Z. And from the processor side, you can see in FPGA how this counter is varying, right? And let's say like you want to create one memory. See, as soon as you add this, right? So this address editor will keep changing. Okay, so right now we don't have any peripheral as such. So as soon as you keep adding this peripheral, so that address editor will be keep changing. Okay, so now I mean let me not add that. This counter value is there. I mean I'm not transmitting that into processor side. In case if I'm transmitting, I need either block RAM interface, GPIO interface, or DMA interface, any of the interface to transmit back to processor side. Okay, but now our objective is to debug this, right? I mean like we want to see that like in board. I mean one way how I can debug in this I can run a simulation, correct? But in this scenario, can we run a simulation? Can I run the simulation? It is difficult, right? I mean, basically this clock is coming from the processor. Do I have processor in the simulator? I cannot simulate the processor. Processor is something like hard IP, correct? Same scenario you will encounter when you are designing high-end systems. Everything cannot be simulated, correct? So let's say like you have one PCB hardcore IP in the FPGA. If you want to simulate that, you have to create a bus function model. Then that creation of the bus function model itself will create the same effort, will have same effort as much as designing new whole IP, right? So in that scenario, what we do, whichever the things are not simulatable, we directly put into FPGA and we see, right? In this scenario, this clock generation, I cannot simulate because processor access I don't have. I cannot simulate the process, right? So then what I can do, I can use something called integrated logic. So in the IP catalog, if you go to the IP catalog and search ILA, you can see integrated logic analysis. So add IP or customize IP. So you can click on customize IP. So here it will ask a lot of parameters. Let me just explain what exactly it does. Okay. So now in FPGA you implemented a counter, correct? So let's say like I mean for simplicity's sake, like I'll have 4-bit counter. Let me take example of 4-bit counter. To observe that, what I do, maybe like I connect this into some LED. If I want to debug this through GPIO, I can connect this whole thing into LED and I can observe how this is behaving. Correct? This is the hardware. One way is hardware observation. Let's say this counter is running at like in our case also 100 megahertz. Will you be able to see this scenario in LED? I mean, like 100 megahertz variation. Can you see it in LED? Is it possible? Yes or no? We will not be able to see, right? It is a high speed interface. And I mean, in this scenario, this is just 4-bit. Let's say like you have 256-bit count. Definitely you will not be able to see. I mean, even with the CRO or any real-time scopes, logic analyzer you can see, but like again, you have to connect all these 256 bits, but then you have to see. But what I can do, these in FPGA, internal to FPGA itself, what I can do, I can actually tap this signal and connect to one module called integrated logic analysis. So if I say that like this has cross 4, this also like say like cross 4. So all these 4 bits will be connected to integrated logic analyzer, and this ILA IP, right? In internally what it does is every clock cycle, whatever the value it observes in these 4 bits, it keeps writing to block RAM memory. Okay, it keeps writing into block RAM memory, and this block RAM memory, it will be read through JTAG interface, and you can see it in real time in your PC. So through USB, you can see it in PC. So whatever is happening in the real time inside the FPGA, this particular counter, how it is behaving, that you can see it in the PC scope, just like your simulator. How the waveform you are seeing in the simulator, right? Same way, in using integrated logic analyzer, in the real time, you can see the waveforms. So this is very important for your debug. Okay. So I mean, like when once you actually implement, you have to understand like how it is behaving in the hardware, correct? So that hardware behavior you can see it using integrated logic analyzer. So the flow is like whatever the IP you have, whatever the design, Verilog design you have, that is connected to ILA IP, and that ILA IP you can connect to block RAM. I mean that this whole thing will be like single, okay, and that internally it sent through JTAG to your PC laptop where you can see your waveform. Okay, so now here it is asking number of probes, correct? The number of probes are nothing but how many signals you have, correct? So right now in our case, how many signals? It is only one signal, right? Counter, which is of 32 bit. So I have only one probe. Okay, this is not bit width. It is that. It is how many signals. Let's say like I have counter one, counter two, and in your FFT case, FFT output. Okay, or like filter output. The filter output can be 64 bit also. So all these signals, basically we are probing. Okay, and this sample depth is again here. Like what is the depth of this block RAM? It is asking what is the depth of this, and you can say that like I can give like highest, right? I mean, so that like I can see larger number of. That is the mistake what we do. Like I mean, some people will give 1 lakh pound, 2 lakh pound. It allows. But what is the drawback of this? Can someone think of it? What could be the issue if I choose larger sample? Can I choose any samples here? I can, provided that much block RAM is available. Because this block RAM also used for your design, right? And the design is larger. You might have used all the blocks, and like 1 or 2 block RAM, like 1024 bits is available. So in that scenario, you cannot use larger size. Okay. So usually you keep as much as, I mean, usually like if you have a block RAM, you can keep larger size so that you will be seeing like more sample. But right now I can be able to see like 1024 samples for every trigger. Okay. And in when you click on the probe, and here I have to say what is the width of my. So 32 is the width of my probe. Okay. Then click OK. So then generate. So any questions? I mean, by the time it generates, if you have any questions, please let me know. Yes. So once you generate this, right, you can see this ILA black box which is generated in your program directory, the hierarchy, right? So, but it is out of the design, right? So you can see these two are separate because you haven't instantiated this ILA in your design. So now if you go to the IP sources, if you maximize this ILA, and here you have something called instantiation template. If you maximize this, so it will say that like what is the template to call this IP. See here, this is the template. Just copy this and go to wrapper and just paste in this device. So ILA, I can say debug counter is the instance, and clock you have to connect with this clock, PL clock. Okay. And one important thing you have to note it here. So this is just sampling, right? Like a ADC. So this ILA is nothing but similar to your ADC. It is just stopping, like sampling every instance with respect to this clock. Let's say this signal, whatever you connect, if it is running more than this clock, so then you will miss the sample. So choosing this ILA sampling is very important. You cannot choose any clock frequency. So it should be either same as that frequency or slightly more than that. Okay. And in the probe, you have to connect this counter. Clear? So now the architecture is something like this. You have processor. From processor, you generated the clock and connected to FPGA. Inside FPGA, you are running counter. And to that counter, you connected ILA. And through ILA, you connected, I mean, internally it is sampling and storing in block RAM, and you can read it in the PC. So this architecture we have built. So now you can generate the bit stream for this. Okay, so it takes around 5 minutes to generate the bit stream. So any questions I can take in between. So you can generate the bit stream. So if you are implementing any project on the FPGA also, please let me know. I can guide you on that as well, and that aspect and related to any questions if you have, right? So you can let me
Sir, I have one question.
know.
I have learned about this SOI instead of SOC. Then I don't know about much about this SOI. How it is different from SOC?
What is the full form of SOI? System on?
Insulator.
Uh, I'm not sure about it. I mean, system on insulator, I am not sure. I haven't worked on that.
Okay, sir. Okay.
Because in the FPGA perspective, we usually use SOC. SOI, I'm
Uh-huh.
not sure. I mean, maybe like, see, actually, I'm mostly expertised in digital part of it. I mean, FPGA, digital design, and
Okay.
RTL design. So anything on analog side, right? Analog, RF, or gallium nitride, all these designs, I'm not much worked on that. Industrial point
Okay.
of view also. Wireless also, I can, I mean, answer any of the question because most of my designs are implementing various wireless algorithms. Initially, I was implementing CDMA-based transceivers, especially for missile and drone applications. So then I
Okay.
worked for various RF synthesizers, then 5G systems, point-to-point network.
Okay, sir. Okay, thank you. Sir, I have started my research on power optimization using artificial
Yeah.
intelligence.
Okay.
Yes. Then what are the challenges is there to implement this AI in VLSI? Can you
So when you
explain?
say power optimization using AI, so
Uh,
I mean during design phase, are you planning? Okay, you are actually identifying what is the power consumption and like you are planning to gate certain part, is it? Like gate the clock, all this aspect, is it?
Yes, sir. Yes, sir.
So what is the scope? Okay. Okay. So again, I mean, like one challenge, what I say that like, see, like you are saying power optimization is using AI. So to implement that AI algorithm on that also causes some power, right? So then like it is a trade-off. So one challenge what you have is like, see, like you are trying to optimize the power. That is true.
Yes, sir.
But to implement that algorithm, AI algorithm in that architecture, again, that consumes power. So whatever the optimization you do here, so that same thing shouldn't be like compensated in the another part. So that you please take care. That is one of the major challenge what I. So
Okay, sir.
and like one thing like what suggestion I have is like the AI is like not solution for all the things. So you
Mm.
clearly identify where we can apply that. And so I mean in terms of design part
Yes,
I
sir.
agree. I mean especially
Uh,
like in case of uh, like power optimization strategies right now Xilinx and many other companies are implementing during like placement and routing. So there they see that like where is the threat for power uh, like power consumption, and accordingly the gating everything they identify during the design stage itself, and in the design they optimize. But let's say like you have already inbuilt device, let's say like your processor, or like let's say in FPGA architecture itself. One of the power optimization strategy what we use is like we just push that into sleep mode, or like we gate the clock to that particular section of the code. But now when we say AI, so your AI will be keep monitoring this, right? So whatever the
yes.
power you save there, so that will be like consumed by this AI. So that you have to be very careful. I mean, you have to
Okay.
analyze.
Yes, sir. Okay, sir. Thank you, sir. Thank you.
Yeah. Any other questions? So I mean, I think like it takes some more time. Just it need to synthesize and implement that. So were you able to parallelly try these experiments what we did today, yesterday, and like last class? So did you install Quarters or Vivado, or like did you use any of your college PCs and try this thing? See, these two subjects, I mean, this particular part, right, hardware, software co-design or reconfigurable computing, this kind of thing, it is not theoretical subject. I mean, like not like just a theoretical lecture what you'll be listening, right? So unless you try hands-on, it is of no use. And you should start putting into the board, and like you start testing hands-on what is happening. Then only you will understand this. And many things, right? Like I mean, you will not find like certain concepts you will not find in like any textbooks or like data kits. Also, many things like as we work on the hardware, then only we understand many of the learnings what I had, that is like by your own experience itself. Like let's say like one of the learning what we say that one of the scenario uh, which I was like working in one of the companies, we had to generate like you all see this noise floor. So how you can generate this noise? So practically it is not possible. Like SNR variation, if you want to do MATLAB and all, you can possible. It's all simulation. But in hardware, how you can generate? So using noisy resistors, everything, like we had built one noise generator model itself. So that kind of scenarios and all, like we did lot of experiments, and like by doing the real time experiments only you'll understand this. Okay, so unless you experiment, it doesn't work. You will not find in any literatures or textbooks. Right. Parthasarathi is asking, how we can actually interface, right now we interface from Zinc Ultrascale, right? But like if you want to interface from the external clock P, clock N. So right now, whatever the board I was showing you initially, so this is the board what we'll be using. So it doesn't have actually external clock to the PLC. Is it visible? Yeah. It doesn't have external. I mean, this is SOM. It is actually processor centric board. In this scenario, only processor side they have connected. But in case, like let's say, like you have uh, the clock which is connected to PL, then what you have to do here, right, in the design, you have to create one XDC file. Okay, in XDC file. So here, in the hierarchy, you can see something called constraint, right? Or like another way I had shown you, like after implementation of that. So here you have to create a new constraint, and in that constraint file, you have to say that like which port you have to connect where. Let me give you an example. Let me just so for let's say like in Z board, okay. In Z board, yesterday I was showing you master XP, correct? So let me just open that master XP. So here, if you search for clock, see G clock, which is connected to Y9. So these constraints you have to put it there. See Y9 and this G clock pin, right? So let's say you have here one port saying clock, like this PL clock 0, that is input port, okay, of your design module. So instead of this G clock, you have to replace with that input port name. So now what will happen is, uh, just show you that. And whenever you run this tool, right? So if your RAM is like 16 GB or less, so it will actually your PC start behaving slow because it consumes a lot of RAM. Uh, yeah. So here, this G clock you have to replace with that port name. Okay, Y9. So the meaning is Y9 pin of the FPGA, you are connecting to a particular port in the Verilog. So that is the meaning of the constraint file. Okay. And one more thing, you mentioned that like the scenarios like clock P and clock N. What is the meaning of that? That is basically a differential clock, correct? It's a differential signal. But inside the FPGA, it is not differential signaling, right? It is basically a single-ended signal. I mean, you cannot have like clock P, clock N, like always at positive edge of clock P, always at negative edge of clock N. That kind of scenario you cannot. So for that, what you have to do, you have to put differential to single-ended buffer. Okay, so here, if you see, there is one language template, one bulb kind of symbol above the code. So if you click on that, so if you search buffer, so you can see various global clock buffers, right? So in that, you search differential to single-ended. See here. So here, like differential is the input, differential N input, differential P input. So output, right? You can basically take one of the output, like P side or N side, or you can also see the clock buffer. So there are various buffers. So you have to ideally choose that. I mean, whichever like suit for your application, that you have to. These are clock buffers. So differential to single-ended. You see, yeah, yeah. I so this is single-ended to differential, three-state buffer. Okay. So this is output. So same way, I buff user, I buff, yes, I buff DS, right? So input is differential, like positive in, negative in. So output is single-ended. Okay, this kind of buffers you have to use. So this what it does is like it will convert your differential ended to single-ended. So when I say differential ended to single end, ideally what it does, uh, the differential signals are like this, right? Positive is this, negative is this. Okay. So ideally inside the FPGA, what I need? I need single-ended signal, right? So input is this, output is single-ended signal, right? So why we do this? Basically, whenever like in the differential signaling, there is a possibility that like I mean in the real time, there is a possibility that like noise gets added, right? So here we will have differential buffer where actually it removes this noise. I mean like same noise gets added to both signals. So whenever I take the difference of these two signals, so this noise gets subtracted, right? But whereas this amplification, I mean this signal will get amplified. So that is the fundamental concept of differential signaling. So you will get like pure clock. And basically, you will not see any noise in the clock signal. So for that, like we usually use differential signal. Okay. Okay. Still it is synthesizing design. So like we basically like if you have any doubts, please let me know. That kind of thing I can explain. Like in terms of like if you're using this FPGA in your research, like if you're stuck at any point, some points you can just let me ask. You can ask me, can help. So in the newer Vivado, also like you have this UVM and also you can test that as well. Like nowadays, like previously, like you used to have like separate tools for UVM and all, right? So in these devices, you have UVM also integrated, like Vivado, latest Vivado. You can run all this Vivado UVM based verification, everything in the Vivado itself if you have a license. Okay. So you can see this like takes a lot of time usually. Like I mean, when because like I have also added this sync SOC, right? It takes some time. So every time when it runs, right, like you can see the if any warning or error, so you can see this in the TCL console. So that will give you the real time scenario, how it is synthesizing, how it is implementing. So usually ILA based design take time to synthesize the whole. Yeah. So one more question from Parth is like he's using Pink FPGA. So like how we estimate the resource in Pink FPGA, right? So here again, the understanding of the separation between software and hardware, you have to understand clearly, right? Uh, Whenever you are running the Python code, okay, that Python code is not running on the FPGA. Okay, so that Python you are running on overlays, right? I mean, if I'm not wrong. So you are creating the overlays, and on top of overlays, you are running the Python code, correct? So the example what we had taken here, right? So that Python part come into processor side. Okay, Python is running on the processor. The pink is actually Zinc SoC, same SoC what I am showing you here, same SoC. So that Python part is running on the processor side. It is not running on the FPGA. So using overlay, they have created a bit file. So some part will be running on the FPGA. Okay. So if you want to estimate, like if you create any FPGA design, if you create your own bit file, then only that resource part will come into picture. Okay, how many lookup table it is consuming, uh, how many block RAMs it is consuming. So whatever the Python you run, let's say like you are running 1,000 line of code or 5,000 line of code or anything, or one line of code, it uses processor. It is not impacting your resource. Resource will be fixed itself for the fixed overlay. So let's say like you are creating any RTL code and putting on FPGA, you are synthesizing on Vivado, then only the resource will come into picture. Hope you are getting the separation between processor and hardware. So that is the main thing. I mean, that is where like I find difficulty in making students to understand in my hardware software code design course. So there are, many are like embedded students, they are into software, but the separation between this processor and FPGA understanding is very important. So where it what part is software, what part is hardware. Okay, so whatever you run Python, C++, everything will be running on the processor itself, not on the FPGA. Through ASCII interface, it will interface to the FPGA and it will be executing. So synthesis is completed. So now implementation is happening. So looks like it reloaded some of the design. Just let me reset the run. Okay. Meanwhile, let me just quickly go through my PPT also, so that I mean by the time it synthesizes, let's quickly whatever like I wanted to present on the ILS, I'll present that. Let this whole thing get implemented. So at the end of all the four session, I'll share you these PPTs also. So I think I have, I'll share it to the madam so that like she can share it to you. So so far actually like integrated logic analyzer in Vivado we have seen ILA, right? So if you go to the Quick Logic is also one of the FPGA vendor. So if you go to that, so you will see like view draw analyzer. Microsemi FPGA, they use some tool called Libero SoC. So in that you will see Smart Debug or Live Pro. If you go to the lattice FPGA, they use Diamond, Radiant. Like I mean, yesterday we seen like Potters and the Viewer, right? That way, like they have their own. So they use some reveal logic. Okay. In Altera, that is Potters time, we have to use something called Signal Tag. Okay. These are the various scenarios. So what is the application? Like I already explained you how to implement. So basically, like it is for IP debugging, internal signal tracing, or timing verification, like how long it takes, protocol debugging. Let's say like you want to debug I2C, SPI, or PCI. So you can use ILA. Okay. So It's basically a logic analyzer inside there. Right? So I showed you that like how that lock RAM connected to FPGA and like through JTAG. Okay. So it is basically post synthesis. Okay, not pre synthesis. So we have seen that like add IP core in Vivado using IP Vivado logic core. Then connect the signals to the probe. We have seen that like how to connect, and then like whatever the signal you want to connect, so you connect it through instantiation, right? So you have to set like how many probes you want, what is the bit width, sample depth, and you have to enable the trigger condition. So you can see this. I mean, like post implementation still running. The synthesis is running, right? So once that is running, I can show you that like whatever it is implemented, like it will tap that signal. That is why actually we say signal tap. So it will just tap the signal and it will display. So basically, you have to analyze in bit file. Okay. So these stages anyway, like we'll see, like once it is generated, right? Let's see. So. Uh, Uh, one more question from Parth is like he verified design on the FPGA board, it worked, but like in the SoC it is not. So that could be interface problem. So what ideally you have to do is like in the whatever you have implemented on the block design, right? We saw that like the block design we created and we interfaced. So usually if this interface is not proper, and when you actually launch using SDK, you have to export here. So whatever we created here, right, address map, everything. So I said like the software part, we have to run it on the SDK. These two are independent tools, right? So to connect that tool, we have to export the hardware. So one file will be generated and sent to the SDK side. So that SDK we call, usually this file we call it as hardware defined HDF file. That is a handoff file. So that handoff file it will use, and it will understand like what configurations you have given in the FPGA here. So that will be like a reference file for it. Accordingly, software related things will be created. We call it as board support package, right? So if this handoff file is not proper, then when you run it using FPGA SDK, that will not proper. You will see the issues there. Okay. So I mean, as a FPGA engineers, right, the most time-consuming part is like synthesis and implementation. So one of the design I work in one of the company, it was taking almost 1.5 day. It was a highly congested design for ultra scale FPGA. The general build time was 1 hour. Depends on like your server capacity also. If you have very high end server, then it was 1.5 day. So if I used to uh, build that in my local PC, so that used to take like 2.5 days. Depends on like your complexity of design, your synthesis and implementation time keeps going high. So this is where like this AI makes difference, right? I mean, uh, so people say that like AI will take jobs, all these things, but in case of like hard deep tech uh, technologies, so many things cannot be done by AI. Mean, let's say like the logical thinking and design aspects and all, it will not be taken care by AI. You need to manually do it because like this is a pre-trained model. I mean, many of the things like which research findings we do it in labs or uh, company. So that is like AI is still not trained for those scenarios. So definitely that will not be replacing these deep tech ideas. Any other questions related to implementation? I hope everybody able to install. Like, I mean, can just uh, give thumbs up in the uh, Zoom that like how many of you installed and started trying this Vivado or the Quarter, or just you are listening theory class from last 2 days. So this is initializing the design. So usually the steps are like synthesize, initialize, then uh, implement, then place and route. Okay. So now you can see this is optimization is happening. So many place and route, after place and route, usually what we have to do is like see like any floating pins are there. So let's say like you have one AND gate. So you have like one FPGA, and you have created lot of circuits like this. Always FPGA tool, what it expects is closed circuit to be there. I mean like this. So these two are inputs, and here you internally you created one wire or register. You haven't connected anything. Like it is keeping like this. Okay. Uh, and you have one more AND gate, and these two are floating. So in optimization stage, what it does, it eliminates this. And ideally, this is like bypass, right? So it also bypasses. So this kind of optimization is there. So many a cases, you'll see that like these things simulation it will run. Even if it is floating, it will run in the simulation. But when you actually implement it in the hardware, right, it will be trimmed off. So you have to be very careful regarding that. Okay. So you have to like understand like which parts are trimming, which actually implemented. So that usually like post synthesis netlist, if you open, right, like that schematic, so you'll see that like which are the pins are there, which are the pins are implemented, which are the pins are trimmed off. So analyzing that part is very important. Okay. So it is running the optimization now. So anyway, the synthesis is completed, right? In that, like you can see the report also. Yeah, utilization report. So if you click on this, so you can see total 32 CLBs used for the logic what we have created. Okay. So total 32 registers. So you can, it is clear, right? Like because basically, okay, this is 32 CLB registers is used. Lookup table only one it is. Okay. So it is clear, right? So because how many bits we use? 32-bit counter we used, correct? And in that 32-bit counter, we basically utilize one of the CLB for logic, for adder. Okay, one CLB for adder, lookup table as a adder, and rest 32 for your counter register, 32-bit counter. So this way it will implement. And one more thing, like this will be clear, right? So like I have added a big processor here, right? But in utilization report, if you see, it didn't consume any resource for it because it already existing as a hard code. Clear? You can see like in this FPGA total 144 block RAM is available. Okay, out of that like 144 like RAM 18, it is actually like 36 kilobits block RAM usually it will be there. Okay, so in that you can basically use 144 for uh, like 54, and that 144 block RAM you can use it as a half RAM also. In the sense, each block RAM is of 36K. You can use 18K blocks. That is why it is showing 288K block RAM and 288 18K block RAM. Okay, and especially in ultra scale devices, we have something called URAM. Okay, so who are like into memory resource research will be knowing that URAM, ultra RAMs, right? It is a very high speed memory. So we have around 64 tiles of this ultra RAM in this ultra scale FPGA. Okay, and if you want to do a high speed arithmetic circuit, you have like 1248 DSP drive. Whatever, like in the first class we were discussing the resources. So the FPGA what I have chosen in that like these many things are. And in terms of IOs also you can see here. Total 189 pins are in this FPGA. Right now I haven't connected anything, right? So you can see that like in this design wrapper, so there is no input output action. So that's where like it is showing in the utilization, 0% utilization in terms of IOs. Okay. And like what are the buffers I was saying, that is also very important. One important thing is like so major mistakes what we do is we keep putting many buffers like differential to single ended, and whenever you see some hold violation you start putting some buffer, right? So as much as possible you use strategy. I mean there are like various synthesizer strategies available, right? So let those strategizers will put the buffer, so you don't put manually. Like let's say like you're driving something externally, in that scenario you put buffer, so in between the designs you don't put buffer, so the tool will take care of putting the buffer. So we have a limited buffer. Let's say like if you want to use PLL, right, in that like only 8 PLLs are multi-mode clock managers, you have 4, and these buffers also very limited. I was say like in one of the scenario, what Parth was asking, like how to convert differential signal to single-ended signal. I said like to use buffer, but how many buffers I can use? Like there are limited, right? So 96 buffers in case of PS, GT, and buff G control I have just 32, right? So we have limited resources. So that is one thing. So in ASIC, I can create like any circuits. I mean because I don't have any boundaries as such. Like I mean. Like there is like size given, but again like I can put any number of netlists, so there is no limitation as. But in FPGA, whenever like I'm designing anything on top of the existing design, right, I have to create these uh, on top of existing resources, I have to create these designs, correct? So that is the challenging thing. Okay, so you have to be very careful on. So you can also see this, what are the configurations you used. So you have some startup tree. That is actually startup tree is something like there are like various pins configurations where like during startup, like based on what it has to start, what had it has to boot. So like you have master data. So whenever you use these things will be enabled. I mean these configurations you can enable using your uh, XDC file. Okay. So you can also see this, they refer it as a black box. Internally, what logic it used, it doesn't say. Correct? So because these are like proprietary IPs, like you can see Zinc Ultra Scale PL, one it is used. ILA you use one. So what logic it also uses logic, right? For sampling, for storing, it uses some logic element. But it doesn't say that like, how it is instantiating, how it is utilized, all this. Okay. So this is actually like when it is synthesizing, right? So usually this report also we usually write some Python or TCL script to analyze if there is any error, right? So this is actually something like it's a messy report. So we usually write report which extract this warning and say that like I mean any critical issues are there. Okay, so this kind of reports we usually automate for summarizing this. See, out of context design, LUT, right? LUT, this ILA, it uses 588 LUT. Even though your design is running some small number of LUTs, but your ILA is taking around 588 LUTs. And memory, it is taking around 104, right? So you have LUT as shift register. These are all like ILA implements. Like this, you can see out of context module runs, not inbuilt design. Okay. So still it is implementing. So that is, I mean, like usually this design implementation synthesis, right? As I mentioned, like when you add this zinc SOC, it takes a lot of fun, drawback. Any questions you have? Meanwhile, I mean, by the time it synthesizes, right? Like we can discuss if you have any doubts or any of the topics. It may take another like 2-3 minutes. So one thing like tomorrow, which we'll be discussing on IPs. Okay. So meanwhile, I mean like you can explore also so that like tomorrow you can come with some discussions like so one IPs are something like let's say like you are designing various RTL codes, right? So, but whenever you actually uh, give that IP, I mean, give that RTL to some other team, some other research team, right? So, what will happen is like they shouldn't know like what is the RTL code of it, correct? So, in that scenarios, what you have to do is like you have to package or encrypt the whole IPs, right? So for that, basically like what you have to do is like you have to create as the IP and send it to them so that like they'll not know like what is the RTL code inside that, right? So it is completely encrypted design. Okay. So one thing like we'll be tomorrow we'll be seeing what are the existing IP. Okay. So let's say here uh, in this, like if you go to the IP catalog, you see a lot of IPs, right? Like Zinc RFSoC IP. You can also see various Vivado IPs. You can also see storage IPs, right? So you can also see uh, like the clocking IPs. So these are the IPs which are built by Xilinx and some third-party vendors. So there are like various companies in Bangalore. Also, we have iWave Designs, Mistral Solutions, Synopsys, Cadence. All these people will be designing IPs. Right? So, but like when they say that like they're giving you the IPs, the RTL will not be exposed. You'll be getting only Netflix. How it is implemented, what algorithm it is used, you will not be understanding, right? So that's how we build the IPs. So in the FPGA also we have various IPs. So let's say like here we have turbo coding IP, like which is I think from one of the Sweden-based company. So recently, like we had discussion with them, like for procuring that. So usually they charge some like 3 to 4 lakh for each IP for the IP design. It's like a RTL. So I mean there are like a lot of potential in this also in from academia. So whenever you say that like you have particular design, it is not restricted only for publication or patenting, right? So what you can do is like you can create your own IPs and you can sell it to the industry, right? Like say like many in many cases I have seen that like very good IPs are coming from the industry, right? Like I mean academia. So like a lot of 5G related, image processing related, so that you can package it as IP and you can give it to industry. Many companies will be buying, or you can list it in the Xilinx store also. Like you can see this is Xilinx IP store. So if you can see here, some of the IPs are done by Xilinx itself. But if you see H2K decoder, H.264 encoder, this is done by SOCtechnologies.com. Right? I mean, that's basically a company. And you can see this multi-layer video controller, which is done by Logitech company. So there are such many companies, external companies who are providing. I mean, you can see communication and networking. There are like a lot of companies are contributing. Xilinx will have their own IPs. Apart from that, like you'll see some other IPs. Also. In especially in Ethernet, I have seen like Bangalore, many companies have contributed. I think, yeah, you can see SOCE that is also external company. In case of networking, also you can see a lot of third-party companies. So almost this is done. I think like displacing the design. Uh, I think like another 1 or 2 minutes it should complete the bit stream generation. So you can see that like it places, then it will route and then it will generate the bit stream. Okay.
Sorry to interrupt you, sir. There are some
Yeah.
questions in the chat box, sir.
Okay. For implementing machine learning or deep learning model, which board will be suitable? Usually like any ultra scale FPGA board, right? So that will be suitable. Again, when I say you want to choose the board, initially what you have to do is like you have to do resource estimation, right? So when I say that like you want to implement one CNN, so first stage what you do is like you synthesize that design, like you can choose any board here, right? So you can choose a board and like synthesize, or any FPGA part and synthesize. So you'll see overall how many resource are required, like I mean, like how many lookup tables are required, how many block RAMs are required. Based on that, you can procure a board. Okay. So usually, like in company also, what we do initially, we'll have, I mean, before choosing the FPGA, most of our RTL design will be ready, and we know that like how many resources are required, or maybe rough estimation. Let's say like for one of the neuron, like in case of convolution neural network or like central neural network. So let's say like you are considering one of the neuron, it is taking some 3 LUTs. Okay. So you know that like how many parameters you need for that particular neural network. So let's say 1,000, 2,000. Accordingly, like it is proportional, right? 64,000 lakhs are required. Something like that will come up. So based on that, which board supports that many lookup tables? Accordingly, you choose that board. So ideally, it is based on the resource, number of IOs. In artificial intelligence, let's say like you want to interface some cameras and all, right? So then you have to see that like whether that board supports camera. For example, this is artificial intelligence supported board. This is also a lower end board. This also you can procure. So you can see here. So it has all the interfaces. So you can see one small camera with it. Because this is Vision AI board. So you can see this, right? So and you can see this PMOD. Here PMOD connector is there, where you can actually connect external sensors. And you can have HDMI connectors are there, where you can connect the camera, this display. And you have two Ethernet interfaces there, where you can actually uh, connect network, right? So like simple Raspberry Pi, right? You can run an operating system on top of this song, and you can run various image processing algorithms. But one suggestion, like apart from the resource estimation, you have to make sure that like especially for the deep learning application, you need um, this one, like the processor. Okay, you always procure the soft board. Okay, not just FPGA board. Any other question? Let me set up the hardware also quickly, so that like I mean once the synthesis is done. So usually the setup is like you can see this FPGA, right? So in this, like you'll have one JTAG port. Okay, JTAG port will be there. So what you have to do is like you have to connect that JTAG port, and then you have to connect to the JTAG USB. Then usually it requires 12 volt power. Okay, 12 volt supply, 12 volt and 1 amp. So you can see it is routing, but like meanwhile I can show you how to connect out. Here you have option called Open Hardware Manager. Right? If you click on that, it will connect to the local hardware, whichever it is connected. So you can open target, auto connect. Basically, it is communicating through JTAG. So Parth had another question in the chat. Do you have any drawback of using operator rather than algorithm to realize any operation? Yes, definitely. So let's say you have one multiplication. Okay. So if you straight away use multiplier operator, you are giving freedom for the tool to choose any of that. So here, like multiplication in the sense like some circuitry will be implemented. So it may not be area optimized or power optimized. So instead of that, like if you use any algorithm for multiplication, let's say both algorithm, right? So you can actually implement that algorithm. So it will be speed optimized and area optimized. Okay. So you have to go for algorithm. I mean, so that like if you will get a optimized design. And now you can see this like device is automatically detected, right? You can see uh, DSP. You can the both the I mean you can, it's not just single hardware which right. So it actually detected Xilinx FPGA XCK26 FPGA part and ARM because it's a SoC. If it is only FPGA, right, you will see only one device and it is saying not programmed. I haven't programmed still. That is why it is showing just uh, just FPGA. I mean not programmed still. And here this is a software side ARM core. So it is doing the routing of the design. Ideally, once the bitstream is generated, right, we have to actually program the device. Like we have to say that like which is the bitstream file and which is the debug probe. Debug probe is like whatever the ILA we have generated, that file we have to choose. Okay. So once that is done, we have to program and see the performance. One more thing, like today we just discussed ILA, right? You can also have the serial IO scans. Like if you want to identify bit error rate, right? If you want to identify what is the clock. So now in the latest devices, we have serial IO rate. I mean, you can plot the eye diagram. Like if you are good at communication, you might be knowing that plotting the eye diagrams. Right? So all these things we can plot it here. So there is a separate IP like ILA called IBERT, okay, which identifies the bit rate, bit error rate, okay, bit error rate, E by N naught. Like these are the parameter usually what we use it in communication, right? So all these things you can analyze. Okay.
Sir, there is a
Yeah.
question. Durga Devi asked how to collect data sets for VLSI circuits to apply ML.
Data sets for VLSI circuit, is it?
Yes, sir. For ML, machine
In the
learning,
sense,
I think so.
I mean, like you are saying in terms of designing aspect or like how, I mean, you are designing a ML application and for that ML application you need data set or VLSI circuits like you want to automate and then like you have to collect the data set, how it is.
No, this is for that already I have asked regarding power optimization, sir. To implement this, so I have heard about we need data sets like that to apply this ML algorithm. That's why.
I don't think actually there is a publicly available data set for this. So maybe you
That's
have to create, yeah, you have to create your own data sets and like possible cases, right? So or like you have to get some like wherever the research institutes are performing these operations, right? So again, like I think this is very tedious job for you, right? Because like
yes, that's why it's
correct,
limited like that. I have.
very limited. Yes, that is true
Uh,
because whatever like especially these kind of researchers, like whoever designing the IPs, you will have this data set, right? So these are proprietary data. You will not get that like how they optimize. Let's say like Qualcomm is designing, Samsung is designing. They are not going to expose you the data set. So either one way how you can do is like you have to create your own data set. with some experiment, and then you
Okay.
feed that into your ML, uh, and like maybe so one ideal way what we usually do is like in some of the application what I'm working, so for the LLM which I'm supporting, so we take help of various interns, so we actually give them like various use case scenarios, right? So we give them metadata. I mean, you say that like this particular application you do this particular simulation, so they will be creating various simulations and emulation with respect to particular data sets like emulations. So what you can do, you can create multiple metadatas using LLMs. So if you tell
Okay.
the ChatGPT saying that like generate 1,000 metadata for me, with this particular case, like for optimization, it will generate various cases. I mean, it cannot generate the actual scenarios. It will generate various cases. Let's say like a getting case, or one of the part is power down. That kind of cases it will create. So those cases, you take help of like any BTech students or whoever in your college or like somewhere who are interested. You ask them to simulate those cases. I mean, now
Okay.
that is a collaborative data set to be there, right? I mean, like let's say like when I say ML, it is not with like some 10, 15 data sets. I need at least 1,000 plus data sets, right? So
Yes, sir.
that is where like this whole challenge of model generation is there, right? I mean, like why India is also facing difficulty in terms of creation of the models as like we need lot of fine tuning. We have a SFT. SFT is required. I mean, like SFT is something like initially we train the whole model with the data, then some human intervention is required, right? Like SFT, supervised fine tuning, all this. There, what we do is actually like we take help of multiple humans itself, and whatever the output generated from the model, we look into that, like whether it is actually uh, working, behaving as expected. So that requires a lot of investment. So just generating, training the model is not sufficient. So if the model has to be thorough, then like this has to be human monitored. Like each response will be human monitored. Like OpenAI, Apple, all these guys, like taking one of the company you can search. There is a company called Turing. I mean, many IITians students are contributing to. I was also one of the contributor for Turing. So where actually like they give like various we get that like pre-release models. So we need to. I was actually contributor for Verilog and VSDL. So where I actually like helping the model to. I mean, model was keep generating Verilog or VSDL codes. So what I used to do is like I used to evaluate that response, and I used to give the feedback to the model saying that like this is a mistake what you have done. So initial OpenAI models used to be like very raw. I mean, like if you generate a very low code, it doesn't understand where to put wire, where to put register. It was a mess, complete mess models. So now, like after like lot of feedbacks from contributors, so it is now getting fine tuned. So unless your model is gone through like initially millions of data sets, it is trained and done SFT, it doesn't. It is not an optimal model. So SFT and this data set collection is the tedious.
Okay, sir. Okay. Thank you for the information, sir.
But
Thank you, madam.
but please go through with the SFT thing. I mean, supervised fine tuning you have to do, else it will not be a proper mode. So now
Okay,
it's
sir.
generated the bit string. So let's program. There is one option called program divider. So if you click on XCK, so now you can see LTX file also chosen, that signal tab file and bit file also. You have to program the device. As soon as you program, So if you open the elaborated design, you open the schematic here. So ideally, right, I mean, once you actually boot the processor, you should be able to see the waveform there. Okay. So right now, I think whatever we have generated, in that, like, we are not getting proper clock. I mean, it happens that, like, sometimes if your USB is not responding properly, right, so you will not get a proper clock. So ideally, you should see the waveform there. Okay. Like the ILA based waveform you should be seeing. So right now I'm not seeing that. Like, let me just, I mean, you can see that program in the hardware manager, right? You can see the, uh, let me just open that. Because this clock is dependent on the processor also. If you do not, I mean, if the processor is hanged at some state, right? I mean, if you do not program the processor, so you will see some issues. Let me just check that part. So if you click on verify device, so it will, you can also see, uh, this mask file we haven't generated. Okay, let me just check that. I mean, later part, I'll just try to see that, like, why it is not coming. Maybe most probably that clock is not getting generated properly. So let me just debug that and show you tomorrow in the first session. So, but I think, like, what will happen is ideally, like, as soon as you see the program device, right? So you'll be seeing the waveforms in real time on the right hand. So that ideally should happen. So right now, I mean, this, it is like not responding. I mean, maybe like some hardware issue, I feel. So I'll just debug this. So if you have any questions, you let me know. Uh, okay. So one of the question what I have is like any suggestion reading SOC based designs. Yes, so there is a book called Zinc book. Okay, so that is from Xilinx itself, Zinc book. So if you have any, if you want a detailed understanding on these SOC based designs, you can refer that Zinc book. Okay. Let me just share the feedback form also. Please do fill it. I mean, yesterday I got only 3 responses, so that is not accepted. So please share the feedback so that it will help us to. One more session is there, so I can actually. It will help me to update my session accordingly. Please do fill, wait and fill that. Uh, just give me a second. Yeah, this is the link. Please share the feedback. So one second. Yeah, this is the link. Please share the feedback. I expect like I mean we have 37 people are there, so all 37 people to fill that, and do let me know if anything need to be added in the tomorrow's session. Tomorrow's is the last session, right? So I'll just cover those topics, whatever you mentioned, and wind up. Okay. Thank you. Anything else? Hello.
Yes, sir.
Thank you. Then we'll wind up the session. Thank you.
Okay. Thank you so much, sir, for this productive session. We will make tomorrow at 10 a.m. for the next session. Thank you so much, sir.
Thank you.
So, dear participant,